So now we want to talk about motion that's a little bit different than the motion that we've been talking about already. If we look at how this basketball is traveling through the air, we can see that it's moving in two directions. It's not really moving straight horizontally, it's not really moving straight vertically. And even if we tried to make this a straight line, eventually that ball just starts going off in some other direction. And so there's no way to really describe this motion in one dimension. So we need to use two dimensions to do that. Okay, now this is a basketball shot at different intervals in time. So probably not a second, but maybe a tenth of a second, and a tenth of a second, and a tenth of a second. So each one of these pictures represents one interval of time, whatever it might be. We don't really care, it doesn't matter. So what we can see is over time, this ball is traveling up to some top point and then coming back down. It's also traveling in a horizontal motion. So we have a vertical motion and we have a horizontal motion that we can describe. So we can break those two motions apart and kind of be able to describe the entire motion in and of itself. Now basically this is a motion map, right? So typically our motion maps again are in some straight line, but this one is going off in different directions. So if we break this apart and talk about the motion going in the horizontal and talk about the motion going in the vertical, that will help us describe this overall motion. So let's start with the horizontal. If we look at the horizontal motion and see how it is moving across in the horizontal, one of the things that we can do is we can just draw some lines. If we start here in the middle and draw a line straight down, what we're going to see is a pattern. See if we can describe this motion in and of itself. Whoop. It's a lot of basketballs. Hopefully I'm keeping this straight, pretty much. Now what do you notice about this motion? This is kind of cool. Probably not what you expected. But if we look at the intervals, if we look at our change in position in the x direction, looks pretty even. It looks pretty constant. And so what we get in that horizontal direction is a constant motion. Now remember, if we have a constant motion, if we have a constant change in position, this means that we have balanced forces. So in our horizontal direction, we're changing the same position every time interval. So we have a constant velocity, constant motion, which means that the forces are balanced in that horizontal direction. Now we can draw a position time graph for this. Let's draw one real quick. So in our x direction, we're moving at a constant velocity. Our position is going to change over each time period. So we're going to have a straight line slope, which means we have a constant motion. Now we can also draw a velocity time graph for this. Okay, here's velocity equals 0. Since we have a constant motion, if we say that this is x equals 0 over here, we are moving further and further away from the x. So we're moving in a positive direction. So we have some constant velocity. Now we can do the same thing for the vertical. Let's see what happens here. We're going to take these points and draw lines. Sort of straight. This is a little bit different. So on the way up, so when we start down here, if we say that this is y equals 0, as the ball moves in the y direction, the change in y is not constant. The change in y gets smaller and smaller and smaller as we go up. So in the vertical direction, it is not constant, which means that the forces on it are unbalanced. So if we draw the position time graph for the vertical motion, we're going to call this y since we're moving vertically. We're getting smaller and smaller. Our change in y is getting smaller and smaller, so we must be slowing down. We must be accelerating in a way that makes us slow down. So we're actually going to look something like this. So our position time graph is going to have a curve to it. And this is showing that we're starting at y equals 0. And as we go up and up, our slope gets smaller and smaller. So we must be slowing down. But if we keep going on our motion, what's going to happen? There it is. So if we continue this motion, what we're looking at, the space that's changing, the y direction is changing so that it gets bigger and bigger and bigger. So once we reach this top point, when we start coming down, the change in y gets bigger. And so that means we must be speeding up. So now we're starting not at y equals 0, but y equals somewhere, I don't know, maximum. So up here at the y is maximum, we're going to start speeding up and going back, oops, I'm going to run out of space, and going back to y equals 0. So here, we're speeding up. And not drawn very well. So in our position time graph in our y direction, as we go up to whatever height the ball goes, we're slowing down. When we come back down, we're speeding up. Now we can draw a velocity time graph for that one as well. Now we defined this as y equals 0. So we are moving away from 0. So that must mean that our velocity is positive. So it's going in the positive direction, but it's getting smaller. So remember on our velocity time graphs, this part up here is positive velocity. This part down here is the negative velocity. We started out with a high rate of speed, and we're going to a slower rate of speed. So we're going to have something that looks like this. When it starts to come back down now, we've changed direction. So now what we're going to be is in this negative part. We're going to start up here and increase our velocity. So when we look at our velocity, this part right here is where the ball is moving up and it's slowing down. This part right here is where the ball is coming down and it's getting faster. I can't seem to spell. Okay, so we're speeding up. So our velocity is getting bigger. We're starting at about 0. We're changing directions. We don't ever actually get to a point where it's 0 velocity, but this is where we're going to change directions and we're going to speed up. Now remember the area under a velocity time graph. So all these areas under here are our change in position. This is our change in y, our change in y, our change in x. So we're looking at those different things and we're looking to see how they change. So if you find the area under the velocity time graph, or the area from the line to 0. So in this case, when we say under, we're talking about this from this line to 0 is going to be your change in position. Let's move this down. Okay, so we can also make an acceleration time graph. So here's our acceleration and our time. This is acceleration equals 0, and when we look at this, our velocity is not changing. If we don't have a change in velocity, it's 0. So our acceleration time graph for the horizontal motion is not very exciting. But if we come over here and look at our acceleration time graph for this one, what we're looking at, our acceleration here is negative. So we are moving up, so the ball is going in a positive direction, but it's slowing down. So we have a negative acceleration. On the way down, we are speeding up, but we're speeding up in the negative direction. So we still have a negative acceleration. So our acceleration is going to be negative the entire time. Now if you think about that, why does that happen? What kinds of forces are acting on the ball? When we let go of the ball, if we were to draw a force diagram for our ball, after it leaves the hand, what's the only force acting on that ball? The only force acting on that ball is the force of gravity. So this entire time that ball is traveling through the air, the only thing affecting it is going to be gravity. And so we know that the net force then, okay, the only force that we have is the gravity. So we don't have a force counteracting that gravity. So the net force is the force of gravity. Notice that we don't have any forces acting in the horizontal. That makes sense because we have a constant motion. There's no forces to change that constant horizontal motion. It is not constant in the y direction because we have an unbalanced force. And that unbalanced force is due solely to gravity. So the net force then is equal to the force of gravity. So we can find the net force acting on a projectile pretty easily. It's just equal to the mass times baby g. Now we can also find the acceleration. The net force is equal to the mass times the acceleration. And we know now that this net force is due to the gravity. So acceleration over here is always going to be negative 9.8 meters per second squared because that is the acceleration due to gravity. Now we can also analyze this motion using a motion map in either direction. So if we talk about our horizontal direction, we know that it's constant. And so we know that our motion is going to be from x equals 0, from over here on the left to over here on the right. We're not going to draw an arrow for each ball. Let's just draw like maybe, I don't know, 7 arrows or something like that. So we're going to go from here. It's going to be constant. 1, 2, 3, 4, 5, 6, 7. So each one of these arrows, again, represents a certain amount of time. So just like this ball over here, the difference between this ball and this ball is a certain amount of time. This ball and this ball is the same amount of time. That's what each one of those arrows is going to represent. In our constant motion, these are all equal. And this is going to be both the change in position and the velocity motion map for the horizontal motion. Now over here we had a 0 acceleration. Since it's a constant motion, our velocity is not changing. So our acceleration motion map, we don't have any acceleration. Our acceleration is 0. So our acceleration motion map is just going to be little dots. Now in the y direction, we want to kind of probably go in the up direction since that's where we're going. If we look at the space between here and here, it's pretty big. And then it gets a little bit smaller, a little bit smaller, a little bit smaller, a little bit smaller. So in our y direction, we can start out, let's see, we had 7. So if we say that the first 3 or 4 are going up, so this is our first section here. This is our y direction and also the y velocity. So the velocity in the y direction. We start out with a pretty high rate, so we have a high change in position. And then we're going to get a little bit smaller. Okay, so this actually gets smaller here. And then we're going to get a little bit smaller. And then a little bit smaller. Okay. So what we've got, as we go up, our change in y position, our change in vertical position is getting smaller. Our change in y velocity is getting smaller. That was what we had over here. We decided we were slowing down. So we're moving in the positive direction. We're still moving up, but we're getting smaller and smaller. So our y change in position and our y velocity on the first half is getting smaller. And then it turns around. So then we're going to come back down. I guess I should have used an even number, huh? So then we're going to come back down. So we're going to come over here and just go this way. So we're going to go down. And then we're going to go down. And then we're going to go, see? I can't hold it still. We're going to go down. And as we go down, okay, on the second part, as we go down, our velocity and our change in position gets bigger. So here, we're going in the positive direction. We're going up, and we're getting smaller. And then here, we're going in the negative direction, but we're speeding up. So if you think about that for just a second, what is happening with our acceleration? Our acceleration, as we are going up, our arrows are getting shorter. So in our acceleration, if it's getting smaller, our acceleration is going in the negative direction. Do the same thing. Whoop. That's wrong. So we're going to go acceleration in the down direction because our arrows are getting smaller and smaller and smaller. So our acceleration is constant. Ignore that too. Our acceleration is constant in the negative direction because as we're going in the positive direction, our velocity is decreasing. Now on the way down, we're going in the down direction, we're going in the negative direction, but our velocity is increasing. So our acceleration is still going to be in that negative direction. I'm having trouble writing those straight. Okay. Our acceleration is still in the negative direction. It's a constant acceleration. If you think back to y, okay, over here, we have our force of gravity is the only net force. So the only acceleration that we can have is because of that gravity. So our acceleration, when we go up and when we come down, these are all going to be the same. They're always going to be in that negative direction. So those are our motion maps. So if we look at this mathematically, in the horizontal direction, we have a constant motion. So really only the equation that we need here, our change in position is equal to our velocity times our time. That's how we describe a constant motion. Now remember, we can write that as final position is equal to velocity times time plus initial position. Those are the same things. We just kind of rearranged that delta x there. In the y direction, Okay, in the y direction, we can use the same kinematics equations that we used before. So we have our change in position is equal to 1/2 of the acceleration times t squared plus VIT. Okay, so that was one of our kinematics equations from our acceleration unit. We also had final velocity squared was equal to 2a delta x plus initial velocity squared. And then we also had velocity final was equal to acceleration times time plus the initial velocity squared. So we had these three equations from our acceleration unit. When we talked about those unbalanced forces, we talked about how those particular equations could be used. Now, since we're moving in the vertical direction, we can change this a little bit. Instead of delta x, we can change this so that we can say delta y. So in all of these, we can change delta x to delta y. We can also change a to baby g, because this is going to be a constant acceleration because of gravity. So this equation here becomes, instead of delta x, we're doing delta y, and the acceleration in the y direction is always going to be the acceleration due to gravity. So we can change this one as well to g y plus initial velocity squared. And then final velocity is equal to gt plus initial velocity. Okay. So we can rewrite these to use them in the y direction. We can just make these a little more specific to the y direction by using the acceleration in the y direction and delta y instead of delta x. It just helps us keep those motions a little bit more separate.